The next few slides are going to show the integrated rate equations that are used in kinetics. Now, when we talk about integrated rate equations, most of you that are watching this podcast are not in calculus. A few of you are. Integration will make sense to those of you who are in calculus. For those of you who are not, you can still use these equations, and we'll go through on how to use them. I would recommend that with each slide that you pause the podcast and write down the equations, both the regular rate law equation and the rate law in its integrated form, and we'll be using those throughout the rest of the podcast. So right now, for zero order reactions, this is the rate law. It's the rate is equal to K times the concentration of, we're going to use A as our representative reactant, but K times the concentration of A raised to the 0 power. You know that anything raised to the 0 power is equal to 1, so the rate is equal to K. The integrated rate law is this: the concentration of A at time t is equal to the opposite of the rate constant K times time plus the initial concentration. For first order reactions, the rate is equal to the rate constant K times the concentration of A. The integrated rate law is ln, which is the natural log of the concentration of A at time, is equal to the opposite of the rate constant K times time plus the natural log of the initial concentration of A. Now, a form that's more useful to us than that is also given to you here. Here it's the natural log of the ratio of the initial concentration of A over the concentration at whatever time we choose is equal to the rate constant K times time. Finally, for second order reactions, the rate law is rate is equal to the rate constant K times the concentration of A squared. The integrated rate law is the inverse, or 1 over the concentration at time equals the rate constant K times T plus the inverse of the concentration of A initial. In addition to the integrated rate equations, we also want to talk about half-life. And the half-life of a reaction is the time it takes for half of the reactant to be used up and converted to whatever the products are. This is especially important in classification of first order reactions that have to do with nuclear decay. And you've probably heard about, someone talking on the news or something about, well, the half-life of uranium is X number of million or billion years. So half-lives are important. They also have a lot of uses in terms of when they use radioactive isotopes in medical uses. So we're going to talk about that later, but we want to give you the half-life equations for each of these type of reactions. So again, I would recommend that you pause the podcast when necessary to go ahead and write these down, because we will use them later as well. So the half-life of a zero order reaction is T 1/2 is equal to the initial concentration of A, the representative reactant, divided by 2 times the rate constant. The equation for solving half-life of a first order reaction is T 1/2 is equal to 0.693 over K, which is the rate constant. Now, one of the things that's unique about first order reactions is that the half-life of the reaction is independent of the concentration. If you'll notice, the equation for zero order reactions, the half-life equation, involved the initial concentration of the reactant. It will as well in second order reactions, but in first order reactions, the concentration, initial concentration of the reactant does not affect the half-life. And here is the equation that solves for half-life in a second order reaction. Here we have T 1/2 is equal to the inverse, or 1 over the rate constant times the initial concentration of the reactant. So again, the first order reaction half-life does not depend on concentration, but both the zero and second order reactions do. The importance of this can't be stressed enough, so we've devoted a whole slide to it. In first-order reactions, the half-life is independent of the concentration. In second-order reactions, the half-life is dependent upon the initial concentration of the reactant. Let's look at a sample problem. The decomposition of hydrogen iodide to its constituent elements is a second-order reaction with respect to hydrogen iodide. The WRT there is not a misspelling, it's simply an abbreviation that means with respect to. The reaction equation is 2HI, decomposes to H2 plus I2, and the value for K for this reaction is 2 times 10 to the negative 20th moles to the negative 1 times liters times seconds to the negative 1. If I were to write this out not on the same line, it would be the same as saying liters over a mole times a second at a certain temperature. So if you'll remember that when something has a negative 1 next to it, it means that if you wrote this as a ratio or a fraction, it would be on the bottom of the fraction. So this would be liters over a mole times a second. On the previous slide, you have the reaction equation and the value for K, and here's the problem we want to solve. If the initial concentration of hydrogen iodide is 0.25 moles per liter, what will the concentration be after 3 times 10 to the 20th seconds? And again, it's a good idea here, if you need to, go ahead and pause the podcast and write the problem down. So, as with any problem we want to solve, we want to write a data table to show us what we know and what we're trying to find. We know the initial concentration of hydrogen iodide, it's 0.25 moles per liter. We don't know the concentration of hydrogen iodide at the time we're interested in, which is 3 times 10 to the 20th seconds, so we'll put a question mark next to it. Our K value is 2 times 10 to the negative 20th liters per mole times seconds, and our time is 3 times 10 to the 20th seconds. So there's a complete data table that we can work with. Now, whenever I have a data table, I want to look next at a base equation that I'm going to use. Because this is a second order reaction, I'm going to use the integrated rate equation for second order reactions, which is the inverse of the concentration at time t is equal to the rate constant times the time plus the inverse of the concentration initial. In this case, the base equation and the working equation are the same, so we're going to substitute quantities and solve. So the inverse of our hydrogen iodide concentration at 3 times 10 to the 20th seconds is going to be equal to the product of our rate constant K, 2 times 10 to the negative 20th liters per mole times seconds, times the time, 3 times 10 to the 20th seconds. That product plus the inverse of our initial concentration of hydrogen iodide, which is 0.25 moles per liter, will give us the inverse of the hydrogen iodide concentration at time. So continuing to solve through for this value, we'll find that the inverse of our concentration of hydrogen iodide at time is 10 liters per mole. And it's not our final answer because this is just simply the inverse of the concentration. We need to find the concentration itself. So to complete the problem, we need to essentially take the inverse of the inverse. We're going to take since the inverse of the hydrogen iodide concentration at time is 10 liters per mole, the inverse of 10 liters per mole will get us the concentration of hydrogen iodide at time. So 1 over 10 liters per mole will give us 0.10 moles per liter, which is the concentration of hydrogen iodide at time. Let's try another sample problem. Here, let's calculate the half-life of the previous reaction using the initial concentration of the hydrogen iodide as 0.25 moles per liter, and again the K value as 2 times 10 to the negative 20th liters per mole times a second. So our half-life equation is T1 half is equal to the inverse of our rate constant times the initial concentration of A. So 1 over the product of 2 times 10 to the negative 20th liters per mole times seconds times 0.25 moles per liter. If you'll notice here, the moles will cancel, the liters will cancel. You're left with 1 over 1 over a second, which is equal to a second. So the half-life of hydrogen iodide, starting with a 0.25 mole per liter concentration, is 2 times 10 to the 20th seconds. Let's do another sample problem. And again, feel free to pause the podcast at any point to write these down so that you can follow along in your notes. Now, we're going to consider this reaction. 4pH3, which I believe is known as phosphine gas, will decompose to P4 plus 6 hydrogen gas. So the reaction is first order with respect to pH 3, and the half-life at this reaction temperature is 40 seconds. Calculate the rate constant K for the reaction and the time required to decompose 65% of the pH 3. Solution, as always, prepare a data table. Our half-life is 40 seconds. No concentrations are given here, but a percentage difference is. So the easy way to deal with this is to just set the initial concentration equal to 1 mole per liter, and then your concentration at time to be 65% less than your initial, which in this case would be 0.35 moles per liter. I chose the number 1 simply for convenience because we're given a percentage and it's asking for time. And we do know that in first order reactions, the half-life is independent of concentration, so it gives me the freedom to choose a very easy concentration to work with. I don't know time. I'm going to have to find that. And I don't know K, and I suspect that I will need K to solve for time because as I look at the integrated rate equation for first order reactions, K is involved. One of the wonderful things about first order reactions is that if I have the half-life, I can find K very easily. K is equal to 0.693 divided by the half-life. So 0.693 divided by 40 seconds gives us a value for our rate constant K of 0.0173 per second. Now that I have K, I can use K in the integrated rate equation to solve for the time. Now, this equation on your slide looks really difficult, but if you examine it step by step, it is not. We've rearranged the equation to isolate time. So on top in this ratio, we have the natural log of our initial concentration of pH 3 over our concentration at time of pH 3, and then that will be divided by our rate constant K. So it's the natural log of 1 mole per liter divided by 0.35 moles per liter, and then the natural log of that ratio divided by 0.0173 per second, or seconds to the negative 1. On top, the natural log of that concentration ratio is 1.05 divided by 0.0173 seconds to the negative 1, gives us a time of 60.7 seconds. If you follow this through systematically, you'll be fine. Watch your units, cancel where you can, and everything will go well. We've come to the end of part 3 of the Kinetics video podcast series. I want to leave you with a quote from Nelson Mandela. "A good head and a good heart are always a formidable combination." Stay tuned for part 4.